So hopefully I'm audible to all of you. So without any waiting, we'll directly start our session. So probably we have already waited 8 minutes, so we'll directly start the session. So hello everyone, this is Vijay Rane. I'm a Prime Minister Research Fellow in IIT Delhi, and today we are here to discuss the some problems based on the topics which are covered in the week 6 of the course essential of the oxidation, reduction, and carbon-carbon bond formation reaction, and the application in the organic synthesis. So today we'll see some of the reduction reactions. Actually, we have already seen few reagents in the last week as well, and today also we'll see some common reagents. So, so before going to start, does anyone have any problems regarding the assignment question? So that we will discuss first. So if you have any problem, you can add that in the comment section or just unmute yourself and tell me the problem. So we can discuss that one here. So we can discuss any problems if anyone have. So any problem here to discuss? So if you don't have any problem, then I will show some of the reducing reagent. In the last week that we have already seen many of the reducing reagents. So I will just open that slide so you can, it will be just a kind of a revision, right? So what we have seen already in the last week. So we have seen some of the reagent, particularly some of them are stereoselective, some of them are the radioselective, as well as the some are the uh, uh, what we can say the some radioselective reducing reagents, and particularly we have seen some nucleophilic reducing agent which include the LiAlH4 or the NABH4, in which the hydride minus ion is the nucleophilic in the nature, and which reduces the different functional group to corresponding alcohols, not necessarily corresponding alcohols, but it reduces the different functional group. So if you look at the example of lithium aluminum hydride, so LiAlH4, so it reduces the many of the functional group, including the aldehydes, ketones, right, as well as the acids or the esters. So we have discussed the mechanism how the reaction works, and if you look at the different functional group, so this is the reactivity of this LiAlH4. So if you look at the aldehyde, if you have the aldehyde, and then it can reduce to the corresponding alcohol, then keto corresponding secondary alcohol, acid to corresponding primary alcohol. So as so you can see here the nitrile for the cyanide group, we can convert that into the corresponding amine by using the two equivalent of the LiAlH4. Similarly, we have seen some example of the reduction reaction. So if you add the one equivalent of the two equivalent of the trimethylamine to the lithium and one equivalent of LiAlH4 in one equivalent. So this equivalent ratio is important in this case. So ester we can reduce to the corresponding aldehyde. And if it is particularly alpha unsaturated ester, it can reduce selectively. That is, it gives 93% of the alpha unsaturated aldehyde in this case. Uh, Further, we have seen some modified version of the lithium aluminum hydride, and which is the lithium trialkoxy aluminum hydride. And in this way, we have seen some sodium borohydride as well as the some modified version of the sodium borohydride. That is the lithium borohydride, zinc borohydride, that sort of reagents. And we have seen some examples. You can see the last week videos uh, uh, to see these more in detail. So we have also discussed the BH3THF, how the BH3THF works, and the reaction of the BH3THF as well as the NABH4 with the different sort of reagents. So what we will do in this today's class. So we'll discuss some more reducing reagent, and which are generally we see in the NCERT books as well as some we have seen the bachelor's our degree. So particularly the reduction of the aromatic compounds. So if you look at the aromatic as well as the olefinic compounds, so if we go one by one, we'll just English that one, just kind of revision. So if we have the H2 nickel, so it reduces the or the reduction of aromatic compounds. So if you have the any kind of aromatic ring, so if you want to reduce the this aromatic ring, so we can use this nickel. So second one is the also this can also use for the reduction of hydrolysis of sulfur compounds. So of sulfur based compound. So this is the utility of this nickel. Further similar reagent is the Adams reagent. So so what is Adams reagent? It is a H2 and PtO2. So this reagent is called as the Adams reagent, and it used for the reduction of double bond. So if you have any kind of double bond, so this reagent is used for the reduction of this double bond. Particularly, let's say here, so this double bond can convert into the single bond, and the addition of the hydrogen takes place on the syn side. But in this case, if you have the some example which has the two different sort of double bonds, let's take example this one. So this is the one example, and we have here this is the R, this R dash. Let's say this. There is a different alkyl groups or the aryl groups, and if you have such examples, so in this case, so if you use this Adams reagent, so it will prefer the reduction of less stereoselective double bond. So in this case, the less stereoselective double bond will be reduced first. So in this case, what happens? So this double bond remains unaffected, and this bond is getting this double bond getting reduced. So in this case, uh, we need to take into consideration if you have the two double bond, which is the highly substituted. In this case, it's quaternary double bond, and in this case, this is the secondary double bond. So if you use the Adams reagent, it will selectively reduce the double bond, which is less substituted. So similarly, if you look at some more reducing reagent for such reactions, so further next reagent is the combination of H2PDC. Palladium is supported on the activated carbon or the charcoal. So H2PDC is also one of the reagent, and we can use for the reduction of the obviously the double bond. So carbon double bond carbon. Second, also it can use for the hydrolysis of benzylic alcohol. Third, it is used for also used for uh, so in this case, you can see so if you have some if you take some example, the reduction of double bond is the in the same manner that we've seen earlier. But if you say we have the benzylic alcohol, so let's say in this case we have such alcoholic groups, and so we have such group. So here in this case, this is the R1 and this is the R2, and let's consider this is a chiral center, a kind of chiral center. So in this case, what happens? The hydrolysis takes place, and the attack takes place on anti side. So anti-addition of this hydrogen takes place in this case. So it will use the anti-addition. So in this way, this reagent also you can use for the multiple purpose, that is for the let's say reduction of the double bond or the hydrolysis of the benzylic alcohol. Further, there is another reagent that is the H2 on the platinum. This is we generally it called as the exhaustive reduction reaction. It is used for exhaustive reduction. So you can see. So if we have any kind of ketone, that can also get reduced. Also, we already know this platinum reduction that also double bond convert into the single bond, right? By the addition of hydrogen, and obviously the addition will be the same side. So further, it can also convert that alkynes. So if you have RC triple bond R, if you have any alkyne, so these alkynes can get further converted into the corresponding, uh, what you can say, we can convert that alkene to the alkanes. So CH2, CH3. Uh, in this case, we already have the R group, so it will be CH2, CH2, and R. So let's say 1 and 2. So in this manner. Further, if you just modified this reagent, so we not this reagent, the reagent that we have seen earlier. So if we, I will just show you. So if we have some reagent combination, which is the H2 and the palladium, which is supported on the CaCO3. So we call it as a, and the lead acetate, lead acetate. So this reagent is called as a Lindlar's reagent. And if you use this reagent, it can use alkyne conversion of alkynes that earlier we seen. So by this using the H2PDC, so we can able to convert the alkyne directly to the alkane. So if you want to stop reaction at the this olefin stage, that is the alkyne stage, if you want to stop this RC triple bond C and this the R dash, if you want to stop this reaction to this double bond stage, right? R, and let's say hydrogen hydrogen in this case. So if you want to stop the reaction at this stage, then we can use the combination of this reagent. So H2PDC supported on CaCO3 and lead acetate. So this is the Lindlar's catalyst, and if you use this Lindlar's catalyst, we can able to stop the reaction at olefin stage. Right, we can able to stop the reaction at the alkene stage, and further, this reagent is specially stop at alkene state. And if you want to have a selectivity, so if you look at this in this case, so there are two possibility of formation of cis or trans. So for that purpose, there are some different reagent combination. So if you want the cis selectivity, then we can use the, so let's say if you want to cis selectivity, then we can use the Lindlar catalyst, that is H2PDC. And if you want to uh, trans selectivity, then you can use the reduction which is we call it the, if you use it in the with the lithium, in that case it will be, we can lithium in ammonia. In that case, we can able to get the trans olefin. So these are the some reagent combination we can use. If you want to select cis selective reduction, then we can one reagent combination, and trans we can use the different. So in this way, we can use the different set of reagent combination. Further, we have already seen the different oxidation reactions, but particularly in the case of the olefins, let's say as we have seen already the example of the alkenes, and we know that if you want to perform the epoxidation on this case, and so it is R1, let's say R2, so different, this is the R3 and R4. So if you want some sort of selective, so here, so in this case, we can see here, I have drawn specially the alpha epoxide, right? So if you want such a stereo selective epoxidation, so in that case, there is another oxidation reaction. So we have just taken this example just to show the how the stereoselective reactions occurs. So if you perform the oxidation reaction up, let's say we have some substrate. So I will take that example particularly. So the epoxidation reaction that we can able to discuss. So let's take the example of the Sharpless asymmetric epoxidation reaction. So if you perform the Sharpless uh, asymmetric epoxidation, so in this reaction, the reagent is the diethyl tartarate. So DET, we call it as commonly, and titanium isopropoxide and tert butanol. Sorry, the this is the peroxide. So if you use this peroxide in the titanium isopropoxide and diethyl tartrate, so particularly depends on the plus diethyl whether it is plus diethyl tartrate or minus diethyl tartrate. You can see the structure here. The plus diethyl tartrate, which has the, if you look at the in this case, if you look at the stereochemistry, this is the RR, and which is natural diethyl tartrate we occurs in the nature, but this is the minus diethyl tartrate is the SS, which is unnatural diol, and we can use this reagent to get the stereoselective epoxidation, whether if you want to plus or minus. So if you, let's take the one of the example. If you have the such alcohols, and this alcohol particularly, if you look at here, it has the alpha hydroxy group, and if you use the plus diethyl tartrate in the titanium isopropoxide and the peroxide, so it will give the, you can see here the beta selective, the epoxide, and in this case inoxidable excess, which is 98%. So 98% inoxidable excess means almost we will get a stereoselective epoxidation in this case. And if you use the minus diethyl tartrate, in that case also we can get the inoxidable excess 98%, well, but it is a alpha directing. So if you look at the stereochemistry of this epoxide, so in the first case, when you use the plus DET, it gives the beta directing epoxide, and in this case, it is alpha directing epoxide. So you can see we can able to get the stereoselectivity in such case as well. So as you already seen in the olefins, if you want to prepare the cis, and if you want to have a trans from the, if you have such alkyne, if you want a cis alkene, then you can different set of reagent, and if you want trans alkene, then you can use the different set of reagent. So in this case also, so the similarly, in case of the epoxide, we have used the plus DET, then we get the stereoselective, that is beta directing epoxide, and if you use the minus DET, we get the uh, alpha directing epoxide. So we can use the different reagent combination. If you look at, go into the some mechanistic part of this, how this stereoselective epoxidation occurs. So this is the mechanism. So this titanium isopropoxide and the diethyl tartrate, it forms an intermediate and a complex you can see here in this case. So this is the complex which is getting formed, and when it forms such complex, when it reacted with our reagent, so you can see here the olefin and the hydroxide. This is the hydroxide which is forms a complex, and this complex, so in this case you can see this complex is getting formed, and when you use the oxygen, the peroxide, you can see this is the peroxide oxygen. So I will just draw with it with the help of some blue. So this is the oxygen comes from the peroxide, and this is the tert-butanol, right? So this is the peroxide of the tert-butanol, and you can see this is the complex getting formed as a result. So in this case, you can see this directing methyl group is away from the complex. It's just a stereoselective. Only it adds in this side, and when you form a complex, and further upon the completion of the reaction, the complex that we are getting in this case, the epoxide we are getting here will be directing. So if, let's say this is the bond, and in this case, the epoxide directing in the plane. So this is also in the plane, and obviously there will be two different functional group in this case, although there is hydrogen and hydrogen, that is CH2OH. So this is the product form after the completion of the reaction. So oxygen transfer takes place on the same side of this titanium complex. As a result, we get the stereoselective uh, epoxide. In the case of minus diethyl tartrate, this will be a different complex, and we get a different kind of product, which is exactly opposite. So you can see. So this is the general mechanism for the diethyl tartrate. And as you see earlier, that using the lithium in ammonia, that we can able to get the selectivity, right? So we'll see there are some lithium reaction with the help of metal or the dissolved metal in the base that can able to reduce the some systems, especially aromatic system. So common name reaction for that purpose is the Birch reduction reaction. We'll see that one as well. So the Birch reduction, we already have some examples, right? So what is the Birch reduction? So here, so we have the aromatic systems, and if you add in this case Birch reduction, the reagent condition is sodium metal, which is obviously the solid. Plus we add it into the triethylamine NET3 in THF at minus 78 degrees Celsius, right? So this is the first step. We add the THF plus the first step to form this one is the add the THF, then add the ammonia, not triethylamine, first the ammonia. So we need to add the ammonia first, so it will form a NaH plus THF the at minus 70 degrees Celsius. And further we add the sodium metal. So after addition of sodium metal, the solution gets blue. So this the blue solution, which is a kind of, so sodium gives the electrons and it forms a blue colored solution. And after that we need to add the benzene, sorry, the aromatic compound. In this case, I have shown the structure of the benzene, and when you add the aromatic ring, so it will get reduced to the, so this, let's say this is R. It depends on the what R group is. So whether it forms isolated olefin or conjugated olefin, so it depends on the R group. So in this case, so if the donating R group, then we have already seen with the what happens with the donating and what happens with the withdrawing R group. So this is happen in the course of reaction. So we add the THF and triethylamine at minus 78 degrees Celsius. Further, we add the sodium metal, and upon addition of the sodium metal, this triethylamine, sorry, the ammonia and the sodium metal form a electrolyte solution, which is a deep blue generally. The indication of deep blue color is indicate the free electron is in the reaction mixture and the formation of this complex sodium ammonia. Further, when you add the compound, it reduces the aromatic ring and depends on the what R group functional group which is directly attached on the aromatic ring. So the compound form in this manner, which has the uh, whether isolated olefin. In this case, you can see here isolated olefin or it is a conjugated olefin. So it depends on the what R group we are adding. So if you look at some other examples of such reagent, so this is the example that I have directly taken. And if you have add so in this case, instead of sodium, we can use the different metal like lithium as well, lithium or sodium. So if you use the lithium in liquid ammonia, that is at minus 70 degrees Celsius. So, and if we perform the reaction on the reaction, the substrate, which has the methoxy and methyl group. So in this case, what happens? So upon reaction, it will forms the diene, right? So this isolated diene, and if you can see here, which is in the conjugation with this methoxy, right? And further, if you add the HCl water and in the diethyl ether, it can able to form alpha beta unsaturated ketone. So that's the further reaction if you perform such reaction on this anisole derivative. So it can able to form the cyclohexanone. So alpha beta unsaturated cyclohexanone. Further, instead of this, if you add the CO2H twice in the methanol, so we get in this case beta gamma unsaturated cyclohexanone. So depends on what kind of a product we want. We can add different set of reagents. In this case, you can see by adding the acid, HCl, water, and in the ethyl ether, you will get the alpha beta unsaturated ketone. But by adding the another reagent, we'll get in the methanol water. So we'll get the beta gamma unsaturated cyclohexanone. So these are the some reagents or the metal based reduction that necessarily we are looking for this reaction in this case. So this is the Birch reduction reaction, and you can see the how the product is getting formed by using this lithium in liquid ammonia. So another the utility of such reagent is the if you add such if you have such starting material. So this is the starting material here, the ketone, and particularly tert butoxide here, right? So if you add the excess of the the sodium metal in the ammonia and in the diethyl ether, and further add the excess of the butanol, it gives the anti substituted cyclohexanone, cyclohexanol. So in this case, you can see. So this is the terbutanol, terbutyl group, and hydroxy group is directing the alpha, and tert butyl group is directing beta in this case. So it and the selectivity, the stereoselective, it's the reduction occurs of this ketone and up to 98%. Right, the stereoselectivity is 98%. So we get the selectively this product. Further, if you add the lithium aluminum hydride on the same compound, which is alpha beta, which is a ketone cyclohexanone, terbutyl is substituted in this case, and particularly in this case, we get the mixture of cis and trans isomer, but the trans isomer, which is about 89%, right? 89%, and cis is 11%. So it's kind of less stereoselective, but the lithium in ammonia is highly stereoselective. So you can see how this sodium in liquid ammonia, that kind of Birch reduction condition is also utilized for the reduction of the ketone and also the stereoselectively. So you can use this reagent condition as well. So this was the sum of the example, and further, if you look at such some problems like multi-steps involved in the one problem that will already it is in the assignment. So I will just take one of the problem. So let's say this is the problem here, and we have given the difference set of reagent, and we have the multiple options are given like A, B, C, D, and further we have the starting material as well as we have product. So which reagent combination is will be used to convert the A into B. So we have to choose the what are the reagent combination. So if you look at the one by one, so we need to have a alpha beta unsaturated acid in this case, right? Here we have the ketone here, and what are the reagent combination given. So if you go step by step, then we can able to see here. So here, if you add the we have this starting. So this is aromatic and double bond O. Further, we have this cyclohexane. And if you use so if you look at, we'll go one by one. So in this case, if you use we start from the first. So which is the Wittig salt, right? So this is the Wittig salt, and in place of butyl lithium. So this reagent is definitely not going to work, because if you add the butyl lithium and this BPH3, this salt, so it will abstract the proton from here, and also there is chances of the ortholithiation. So this both proton will get going to abstract by using the butyl lithium. So definitely this reagent combination is not at all good combination. So whichever reagent have the in the addition of the butyl lithium at the first step, so it's definitely not good reagent. So you can see this is the wrong option, obviously, because there are these two hydrogens here. So if you by using the usage of this butyl lithium, it definitely going to abstract the proton, and then again if it abstract this proton, so the same molecule the contain it once it form the enolate, it can easily attack another molecule like aldol type addition. Further, the butyl lithium is also nucleophilic. So the butyl lithium can directly show the nucleophilic attack on the carbonyl. So that's why this reagent combination is not good. Further, if you look at the another option, this is the LDA. Now here in this case, LDA is radioselectively attack the proton, and LDA is not at all nucleophilic. So in this case, it abstracts the proton, but what happens? It gives the followed by the aldol type reaction because it abstracts the proton from one molecule. It can react with the another molecule of the same material, right? So this is also the wrong option. So the option number 1 and 4 is obviously the wrong. Further, if you look at the another set of reagent, so in this case there is NH2, NH2, and NH2 same. So we'll go further. So what happened? This NH2, NH2, it forms a N and NHTS, right? So this is just imine formation, right? And further, if we add the another in the both the case, butyl lithium, two equivalents up to here is same. Obviously, if it abstract the butyl lithium, so now in this case, uh, it will selectively abstract. You can see here, although there is chance of oscillation, but it's a imine. So in that case, it's basically dominantly abstract the proton and follow gives the formation of. So here it will gives the once is abstract proton, the invalid getting formed, right? And this double bond is forms here. So this is the product getting formed in this case. And further, we have added two equivalent of the butyl lithium, right? So it can, so once this bond moves here, so this tosylate also gets removed and it forms a NH, right? So I will just take it on the another slide, right? Right. So here is okay. Now it should be the hydrogen because once it forms a double bond, so it will be a this tosylate gets eliminated, and now another abstraction of the another proton, it leads to the formation of, so another butyl lithium is, so it abstract the another proton which is like located here. So once this proton is abstract, this goes here and it forms an anion in this case here. So now the anion located on the, so lithiation occurs at this stage. So because lithium is already there in the uh, reaction mixture, so this is how the anion gets formed. And further, uh, this another what are the options? There is the CO2 and the DMF. So among these two, we need to select one. So if you add the CO2, it will leads to the formation of acid, right? And if you add the DMF, it will be some different step. So if you add the C double bond O, double bond O. So if you add this CO2, it will gives the C double bond O OH because after attacking this minus on the carbonyl carbon, further followed by the abstraction of proton, which is obviously in the solution and from the reaction mixture. So it gives the acid, right? upon hydrolysis. So at this stage it will be a negative, and upon hydrolysis it will form the upon workup it will form the acid. So right, so this reagent combination among this, the option C is the correct option here, because how we have neglected the first option. The first option, which has the direct use of butyl lithium, which is a nucleophilic, right? So it can directly attack on the carbon carbon. So definitely this butyl lithium is not at all good reagent combination. Further, the next reagent combination is the LDA. So when we add the LDA, it will abstract the proton, which is this alpha proton, and followed by it can able to directly attack on the same molecule, or also it can able to attack the reagent that given. But the addition takes place at this stage, that's alpha to keto group. We want the addition attack of the ipso, right? The acid should be at the ipso position. So that's why this another reagent combination is also wrong. So among these two, the first step was the common. Also, the second step was also the common, followed by whether we have to use the DMF or the acid. So if you want to the aldehyde group, in that case we can able to use the DMF. But we want acid group, so we use the CO2. So that's the basic difference between these two reagent combination. So the DMF can lead to the, and the CO2 can lead to the acid. So so the option C here is the correct option here. So this is how you can able to solve the remaining some problems which are already there in the similar concept. So I have just changed some functional group and the reagent combination. Further, if you have, I have selected one of the slide which has the in this the reactivity of the epoxide that we have already prepared in the few before this question. So we have the epoxide, let's say. So how this epoxide behave with the different reagents? So you can see here. So if we have NaOH water and the heat, then this epoxide it get from the diol 1,2 diol, right? So the attack of NaOH takes place on the side which is less substituted. So this is the less substituted site, and this is the highly substituted site, right? So NaOH and water, and upon heating, the epoxide opens from the side which is less substituted. Further, if you add the sodium methoxide, so in this case also the attack of the methoxide uh, or the methoxide takes place on the side of less substituted. Attacks takes place on less substituted side. The methoxide is also on less substituted side. Further, if you add the dimethylamine, so if you add the dimethylamine, the attacks takes place on the again less substituted side. So if you have such nucleophilic reagent like NaOH or the methoxide or the dimethylamine, in that case epoxide opens on the less substituted side from the less substituted side. Further, if you add the LiAlH4, again the same case, the hydride minus attached to the less substituted side. Also, if you use the Li2 NiBr4, that's the nickel-based reagent, and the bromine, its nucleophilic bromination occurs, and the Br minus attacks on the here as well. And further, if you add the copper in lithium, that is the we call it as a RCu Li, in R2Cu Li, that is the nucleophilic alkyl, that nucleophilic alkyl addition also takes place at the less substituted side. So preferably, if you add such reagents, the attacks always takes place from the less substituted side of the epoxide. So you have seen the methanol, sorry, addition of the NaOH as well as the methoxide or the diethylamine or the lithium aluminum hydride in the Li ET3BH lithium aluminum hydride or the lithium triethyl borohydride, both give the hydride transfer to from the less substituted side. So most cases, or in this case, that example, that reagent that I have given, attacks always takes place from the from the epoxide on the less substituted side by using this reagent. So there are some other reagent which can favor the attacks on the more substituted side, like if you use the acid. So what happens? So I will show the exceptional example, like from the epoxide. This is the RHH. And if you use the R dash and R double dash, so if we use here acid, so what happens? The protonation occurs across this epoxide, right? So in this case, the protonation occurs, right? And what happens? So this epoxide gets open, but now it gets open from the side by which epoxide was highly substituted because the stability of this cation. So you can see this cation form is highly stable because it's a tri-substituted tertiary carbocation. So that's why it is highly stable. But if you opens it from the side, so now this carbocation is primary carbocation, obviously due to the stability reason. So in this case, the epoxide open from the side which is highly substituted. So in this way, we can able to tune the opening of the epoxide, whether using the basic reagent or the acid reagent, and we can able to depends on the what product we required. So in this case, we have seen the many examples in which the epoxides get open from the less substituted side, but these are also some reagent. By using this reagent, we can able to open the epoxide on the more substitute side. So particularly if you look at the key difference in the both the cases, so the difference that I want to highlight here. So if you see this all the example, in the all the cases, the reagent combination, reaction condition is the basic in nature. So that's why the opening of the epoxide takes place from the less substituted. Also, the attacks of the reagent is generally in most of the cases, or we can say the all of the cases, is SN2 manner, right? The simultaneous attack as well as the simultaneous breaking of the CO bond takes place. That's why it will be the SN2. But in the case when you use the acid, the attacks goes via SN1 manners. So that's why the opening of the epoxide occurs in this way. So you can say you can look at this basic the key difference between the how the epoxide is open depends on the reaction condition or the solvent also. So how it we can get the different type of alcohol using the different condition by opening of the epoxide. Further, let's say we have some examples here. The again the radioselective epoxidation, and in this case also you can see we have used the MCPBA, and particularly in the chloroform MCP, when we have used the metachloroperbenzoic acid and the CF3 C double bond OH, that is this also per acid, trifluoro per acetic acid, right? And in this case, when you use the alpha unsaturated, sorry, the alpha hydroxy olefin, then we get the selectively the syn, the hydroxy group and the epoxide group will be on the syn side. That is, in this case, you can see both are beta directing, right? So this is due to the intermediate step which is formed while the epoxidation of the olefin. So this is the intermediate step which has the so this is the intermediate step, and let's say and here let's say we have the double bond here, right? And this is the another single bond. So this is the one carbon, the first carbon, the second carbon, third carbon is here, fourth, fifth, and the sixth carbon. Now you can able to visualize, right? So this carbon is from the back side, right? You can see I will draw just with the different. So just to better visualization, I will just draw this bond which is on the below the plane, and further another bond which is this double bond, right? So you can see this cyclohexene get present in this manner, and we have the hydroxy group which is the directing. Let's say it is alpha directing here, so the beta directing. So this hydroxy group forms a, a complex hydrogen bonded complex with the peroxide. In this case, metachloroperbenzoic acid or the trifluoroperacetic acid. Both in the both the cases, it forms a complex which is hydrogen bonded. So this is the And if you look at this is the this is the OH which is going to transfer, right? If you look at this OH, so this OH which comes from the per acid, and this OH leads to the formation of such bonds. So in which, so this is the bond formation takes place, and this directing on the to the same side to the direction of the hydroxy group. So this is how we can able to get the stereoselectively formation of epoxide when we have the hydroxy group. So when we have the hydroxy group which is directing to the beta, the epoxide form is also the beta, and the enantiomer selectivity you can see it's 98% enantiomer selective, right? Further, also you can see some with the some more complex example. In this case, we have this somehow it was the teams was sorry meeting was disconnected. I will start again. All right. So if you take the another example, this recording already started, right? So if you have some such another example which has the two hydroxy group and both are beta directing using the MCPBA, you can see here. So the epoxide form which is also the beta directing epoxide. Further here the another example which has the hydroxy group which is directing to the alpha, we get the product which is alpha directing. So depends on the direct the direction of the hydroxy groups. So the epoxide form in the same direction. This is because the intermediate forms in this manner. All right. So this was the some example that I have shown for the reduction. Also, some example is particularly for the epoxidation of the radioselective, how the stereoselective radioselective reactions work. Particularly, we have seen the example of the Lindlar catalyst and the also the in the Birch reduction reaction. Also, we have seen how the cis and trans olefin we can get by using from the alkyne. Also, the epoxidation using the diethyl tartrate as well as the metachloroperbenzoic acid, that this sort of reagent. We see how we'll get the radioselective epoxides. So if we have the hydroxy group at the alpha position to the olefin. So we can see some more examples. Let's say there are many more examples, many reactions. It's like organic chemistry is like the one single reaction condition. If we perform on we can perform the same reaction condition on the thousand of substrate, and it gives the different kind of react. Depends on the what are the functional group and adjacent side group which had the molecule have. So we'll see some sort of reagents. So particularly the professor already covered the K selectride, L selectride, right, using the NABH4. So that's already covered. So I don't think we need to discuss more that one. Here also the many cases we have mentioned the initial selectivity, that one. So that also you should, I think if you have a basic course of the stereochemistry, then that course will definitely cover that how the enantiomeric excess, that sort of terminology are used, and what is enantiomeric excess. So I will just show briefly. Let's say we convert one reaction A to convert into the B and B plus and let's say B minus, right? So that is just like it has the S compression and it has the R compression, right? So in that case, if we got this in the 60% and let's say 60% and this we got in the 40%, right, in the product. So how much is the enantiomeric excess in this case? So the enantiomeric excess will be in this case the 60 minus 40. How it will be? It will be 20. So the enantiomeric excess will be 20% here because this 40 and the 40 from this is 40 and the 40 from this, both are 40 plus 40. This get racemized, right? And that's why the optical rotation due to this both 40/40 it will be zero. But whatever the is excess, that is the here in this case the 20%. So that 20% is the enantiomer excess in this case. So that probably you should aware about the enantiomer excess. Further, there are from the next week probably we'll gonna see the multiple carbon-carbon bond formation reactions, and particularly that reaction we're gonna see multiple reagents or multiple coupling reactions also we can able to potentially able to see in the next course next week in this course. So there are some oxidizing agent also we have already seen, reducing reagent also we have already seen. Some specific example of the Birch reduction reaction that I will show, which is particularly useful. And let's say the Birch reduction of the such compound, which has the, so if you add the Birch reduction, then in this case we get the hydrogenation occurs here. So this is the product with the Birch reduction. Also, this pyridine type of derivative, particularly upon the reaction, we get the, let's say we have such derivative. In this case, we get such compounds using the same reaction condition. Also, this is the one of the example, and it is direct. I have directly taken it from the paper, so probably you should able to find out how this occurs. So if you have such reaction, so in the case we have already seen, the first case, if you have such by what you can say aromatic compound, and in which one ring is the pyridine and one is the benzene, right? The preferential reduction occurs on the pyridine ring. So in the pyridine ring that we've seen already 1,4 addition takes place. Further, and upon hydrolysis of this one, so we will able to get the CH3, this product when you add the H3O, that acidic hydrolysis. This is gonna occurs because the in the acid hydrolysis we generally see the Birch reduction last step is the addition of NH4Cl, so it's acid hydrolysis. So in this case, upon acid hydrolysis, so in the first case it was not occurs, but when you use the normal pyridine, and in that time the upon the Birch reduction, this is occurs. Further, if you have such a ring in which the one is the benzene ring and another is the pyridine ring, not pyridine, another is also the benzene ring. But in this case, what's the difference? The hydroxy is substituted at this position. So in that case, the preferentially the reduction occurs on the benzene ring, not on the hydroxy, because the reduction occurs on the first step. You can able to recall the first step is the donation of the electron. So obviously the donation occurs on the ring which is electron deficient, right? So in this case, the ring, this the benzene ring is electron deficient, which has the no any group, but the second ring has the ring B has a hydroxy group. So that's why the reduction of the A ring occurs. So because electron deficient ring, that's why the first ring was A ring was the electron deficient. That's why the reduction occurs on the A ring, and this is the product form in this case. So these are the some examples that you should remember. So how this Birch reduction occurs on the different case. Further, so if you don't add the alcohol, the Birch reduction reaction is generally slow, and this Birch reduction also can be useful for reduction of the alpha beta unsaturated ketones. So it can reduce the olefin to the corresponding uh, alpha beta unsaturated ketone to the ketone. The olefin reductions occur using this Birch reduction reaction condition. So these are the some problems or some examples of the burst reduction that you should remember. All right. So we know the boiled blank reduction also. You can able to you should search that, Google it. So you will get to know what is the boiled blank reduction reaction. Also the asylum condensation. That's also the use of the. We can discuss that one as well. What is the asylum condensation? So in asylum condensation, so two equivalent of R, the blonde, let's say here R, and sodium metal in xylene. So what happens? The the sodium metal, as you know, we use the radical, right? So it gives the radical here, and the two equivalent of radical. This is occurs after the completion of the reaction. So this is the asylum condensation reaction, and there are some other examples like Dakin condensation that probably is not like much utility. So you can just search that on Dakin condensation. What are the condition of the Dakin? So it's just like aldehyde converted into the corresponding alcohols using the Dakin condensation. So particularly, uh, these are the some reactions that we already discussed. So Simonson reduction is also one of the reduction reaction that I will just revise this one. So if you have such compound which has the ketone, and you can use the zinc amalgam in HCl acidic condition. So in that case, we can able to get the CH2 R dash. So this is the Clemenson reduction. And again, there is again another reagent is the another condition is the Wolff-Kishner reduction. So in the same reaction, only the basic condition, so which is like NH2, NH2 in KOH. So the product is the same. So this is the two different reaction conditions. So it's one is the Clemenson and another is the uh, Wolff-Kishner reduction reaction. So both give the same product from the same starting, but the condition is the different. One is the acidic condition, right? And this condition is the basic. So if we have the R group has the any acid sensitive group, then in that case we can use the Clemenson reduction. And when we have the some group which has like any of the alkyl is the or this R group is the base sensitive or the acid sensitive, then we can use the Wolff-Kishner. So it depends on the what our uh, starting material are, and the product in the both the cases will be the same. So these are the some reducing reagent that we have already seen. So I think it's good enough for today. So remaining any if you have any doubt that we will discuss right now. So or if you don't have any doubt, then you can able to leave the meeting. So you can put that in the comment section if you have any doubt. So I will take that doubt.